Tonight, we're going to find out exactly how far a human being could actually travel in space. Not where our probes have gone, or where our telescopes can reach, but a person in a ship moving through space. How far can they go before physics, engineering, or time itself says no? The answer is not what most people think. And the gap between what we can do right now and what the laws of physics allow is so large, it will change how you think about our place in the universe. By the end of tonight, you're going to understand every tier of that ceiling, what we can reach today, what opens up with each leap in propulsion, and where the hard wall actually sits between us and the stars. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The honest starting point is uncomfortable. Right now, in 2026, the furthest any human being has ever physically traveled from Earth is about 250,000 miles. That's the moon. 12 people stood there between 1969 and 1972, and that record has stood for over 50 years. Nobody has gone further, not by 1 mile. So, when someone asks how far humans could ever travel in space, the first thing to understand is that we're starting from almost nothing. We have one data point: the moon. Everything else is a question of what comes next. Mars is where the near-term conversation begins. At its closest approach, Mars sits about 34 million miles from Earth. Getting there with current chemical rockets takes 6 to 9 months each way. The physics of the transit, the radiation exposure in deep space, the microgravity toll on the body, the logistics of manufacturing return propellant on the Martian surface, none of it is trivial, and none of it is fully solved. But the mission is physically achievable with technology that either exists or is close to existing. Mars is the next door. It's about 34 million miles away, and we haven't walked through it yet. That's where the ceiling sits today. 34 million miles, which is already roughly 136 times further than any human has ever been. But the question isn't just where we could go today. The real question is, what happens when you change the propulsion? Because every propulsion tier unlocks a completely different map of where humans can go. And the differences between those tiers aren't incremental. They're categorical. So start with what we have. Chemical rockets burn fuel and oxidizer in a combustion chamber. The hot gas expands and escapes through a nozzle. That escaping gas is thrust. It's been the fundamental mechanism of every crewed spaceflight in history. From Yuri Gagarin in 1961 to the crew of the most recent International Space Station mission. Chemical rockets are genuinely impressive machines. One of the most advanced rocket engines flying today, SpaceX's Raptor 2, produces roughly 230 tons of thrust at sea level. The Saturn V, that carried Apollo crews to the moon, generated about 35 million newtons of thrust from its first stage. These are extraordinary feats of engineering, and they hit a wall that no amount of engineering refinement can fully overcome. The wall is the chemistry. The energy stored in chemical bonds, hydrogen and oxygen, methane and oxygen, kerosene and oxygen, is fixed by nature. You cannot get more energy out of a combustion reaction than the chemical structure of the fuel allows. And that ceiling on energy density means a ceiling on exhaust velocity. And exhaust velocity is what determines how fast you can ultimately go. The best chemical rockets achieve a specific impulse, the efficiency measure of rocket engines of around 450 seconds. That translates to an exhaust velocity of roughly 10,000 miles per hour. It's enough to escape Earth's gravity. It's enough to reach the Moon in 3 days. It's enough to get to Mars in 6 to 9 months. It is nowhere near enough to reach anything beyond Mars in any timescale that a human crew could survive. Jupiter sits an average of 483 million miles from the Sun. With a chemical rocket, a direct crewed mission to Jupiter would take roughly 6 years one way. 6 years in the radiation environment of deep space, in microgravity, in a confined vessel, with no resupply and no abort. That's not a mission. That's a sentence. Saturn is 886 million miles from the Sun, on average. Neptune sits nearly 2,800 million miles away. Chemical propulsion doesn't scale to these distances for crewed missions. The physics simply doesn't allow it. So the first tier above chemical rockets, the one that serious researchers are actively developing right now, is nuclear thermal propulsion. The concept isn't new. NASA built and tested nuclear thermal rocket engines in the 1960s and early 70s under a program called NERVA Nuclear Engine for Rocket Vehicle Application. The engines ran on nuclear fission. Instead of burning chemical fuel, the reactor heated liquid hydrogen to extreme temperatures and expelled it through a nozzle. Because the hydrogen could be heated far hotter than any combustion process allows, the exhaust velocity was much higher. Nuclear thermal engines achieve specific impulse values of roughly 800 to 1,000 seconds. That's roughly double the best chemical engines. The NERVA engines were tested at a facility in Nevada. They worked. They ran for their required durations. The technology was validated on the ground. The program was cancelled in 1973 when the political will for ambitious space programs evaporated after Apollo. Not because the engineering failed, because the funding did. NASA and DARPA have recently announced a renewed effort called Draco Demonstration Rocket for agile cislunar operations, specifically aimed at flight testing a nuclear thermal engine in space. If that demonstration succeeds, nuclear thermal propulsion moves from ground-proven to space-proven for the first time. What does nuclear thermal propulsion actually unlock? For Mars, it cuts the transit time from 6 to 9 months to roughly 3 to 4 months. That's meaningful. It reduces radiation exposure during the transit, reduces physiological degradation, and opens trajectory options that chemical propulsion can't access. But nuclear thermal propulsion doesn't fundamentally change which destinations are accessible. A nuclear thermal spacecraft heading to Jupiter still takes years. To Saturn, more years. The outer solar system is still effectively out of reach for a crewed mission on any human timescale. Nuclear thermal is a better tool for the same map. It doesn't redraw the map. To redraw the map, you need nuclear pulse propulsion. But before we get into the propulsion tiers, there's a number that anchors the whole conversation: the speed of light. Light travels at approximately 186,000 miles per second. In 1 second, a photon could circle Earth's equator about 7.5 times. In 8 minutes and 20 seconds, it crosses the 93 million miles between Earth and the Sun. In 4 years and 3 months, it crosses the distance from the Sun to Proxima Centauri. Nothing in the known universe moves faster than light. Not particles, not energy, not information. Einstein's special theory of relativity, confirmed by every experimental test ever designed, says that as any object with mass accelerates toward the speed of light, the energy required to push it faster increases without bound. The last few percent of the gap between any massive object and light speed costs more energy than everything before it combined. The speed of light is not a barrier that better engineering can break through. It's a property of space-time itself, which means every crewed spacecraft ever built, and every crewed spacecraft ever designed, and every crewed spacecraft ever theorized within the framework of known physics is constrained to travel slower than light. That constraint, combined with the distances between stars, is what makes interstellar travel the hardest physical problem humanity has ever set itself. The nearest star is 4.24 light-years away. At the speed of light, you'd get there in 4 years and 3 months. At 10% of light speed, you'd get there in 42 years. At 1% of light speed, about 420 years. At Voyager, one's current speed, a fraction of a percent of light speed, 70,000 years. Everything about the question of how far humans can travel hinges on what fraction of light speed you can achieve with propulsion technology. And every fraction of light speed you add comes at a cost that grows faster than linearly. This is why the propulsion tiers matter so much. Each one doesn't just add incremental speed. Each one represents a qualitative shift in what destinations exist on your map. It's also worth being precise about what the solar system actually means in terms of scale, because most people carry a map of the solar system in their heads that is dramatically wrong in terms of distances. The familiar diagram, the Sun in the center, Mercury, Venus, Earth, Mars, then a gap, then the gas giants spaced out evenly, is not drawn to scale. It can't be. If you drew the solar system to scale on a piece of paper with the Sun the size of a period at the end of a sentence, the nearest edge of the page would be somewhere around Jupiter. Neptune would be off the edge of a desk. Pluto would be somewhere across the room. And the outer edge of the Oort cloud, the true gravitational boundary of the solar system, would be somewhere across the city. The actual solar system is almost incomprehensibly large by any human standard. Neptune sits an average of about 2,790,000,000 miles from the Sun. At 38,000 miles per hour, Voyager's speed reaching Neptune from Earth takes roughly 12 years. Pluto, at roughly 3,600,000,000 miles from the Sun at its current position, would take about 10.5 years at Voyager's speed. And these are destinations within our solar system. The heliopause, where the Sun's solar wind is stopped by the pressure of the interstellar medium, sits at roughly 100 astronomical units, about 9,300,000,000 miles from the Sun. Voyager 1 reached it in 35 years of continuous travel. That's within the solar system. In the broadest sense, beyond the heliopause, the interstellar medium begins. The region between stars, almost completely empty. No sunlight. No solar wind. Temperatures near absolute zero, far from any star. The full galactic cosmic ray flux arriving unimpeded from every direction. It is the most hostile environment humans have ever contemplated traveling through, and it extends for 4.24 light-years in the direction of the nearest star. Understanding that scale is essential to understanding why each propulsion tier matters and what it actually changes about the map. The rocket equation is the most important piece of mathematics in the history of human spaceflight. It was derived by Konstantin Tsiolkovsky in 1897, long before any rocket capable of reaching space had been built. It describes a fundamental relationship between a rocket's exhaust velocity, its mass ratio, the ratio of initial mass, including fuel, to final mass without fuel. and the velocity change it can achieve. The equation is unforgiving. To go faster, you either need higher exhaust velocity or a better mass ratio. Improving the mass ratio means either more fuel or a lighter spacecraft. More fuel means more mass to accelerate. More mass means you need more fuel. The ratio spirals. For every kilogram of payload a chemical rocket delivers to orbit, it needs roughly 15 to 20 kilograms of propellant at launch. For interplanetary missions, the ratios get worse. For interstellar missions, chemical rockets fail entirely. The propellant mass required to accelerate even a small payload to 1% of light speed would exceed the mass of the Earth. Not figuratively. The mathematics actually produces a number in that range. Chemical propulsion is not a slow interstellar technology. It is not an interstellar technology at all. This is why exhaust velocity is the key variable. Higher exhaust velocity means more velocity change per kilogram of propellant, which means more capable missions per unit of propellant mass, which means missions that were mathematically impossible with one propulsion system become possible with the next. Chemical rockets achieve exhaust velocities of around 10,000 miles per hour. Ion drives achieve exhaust velocities of 100,000 to 350,000 miles per hour. Nuclear thermal engines achieve roughly double chemical, around 20,000 miles per hour. A fusion rocket operating at high efficiency could achieve exhaust velocities approaching several percent of the speed of light, on the order of millions of miles per hour. Antimatter annihilation could theoretically push exhaust velocities above 10% of light speed. Each step up in exhaust velocity is a step up in what missions are physically achievable without requiring absurd propellant mass ratios. And each step up requires a fundamentally different energy source, because the energy released per kilogram of propellant is what determines the exhaust velocity. Chemical energy, electron volts per reaction. Nuclear fission, millions of electron volts per reaction. Fusion, tens of millions of electron volts per reaction. Antimatter annihilation, the full mass energy of the particles, hundreds of millions of electron volts per reaction. This is why the propulsion tiers aren't arbitrary categories. They're different energy regimes. And each regime represents a qualitatively different level of access to the solar system and beyond. Understanding this is understanding why the question, how far could humans travel, can't be answered with one number. The answer is, it depends where you are in the propulsion hierarchy. And right now, we're near the bottom. We've barely left the first rung. There's a propulsion concept between chemical rockets and nuclear thermal that deserves a moment of honest attention. Ion. Propulsion. It's not theoretical. It's been flying in space for decades. Ion drives work by ionizing a propellant, most commonly xenon gas, and accelerating the resulting charged particles using electric fields to very high exhaust velocities. The efficiency, measured as specific impulse, is 3 to 10 times higher than chemical rockets, depending on the design and available power. NASA's Dawn spacecraft used ion propulsion to travel to the asteroid Vesta, orbit it for over a year, then leave Vesta's gravity entirely and travel to the dwarf planet Ceres and orbit that as well. No spacecraft had ever before used propulsion to change orbits around two distinct solar system bodies. It was only possible because ion propulsion stretched the propellant budget far enough. The ESA's SMART-1 mission used ion propulsion to reach the Moon Japan's Hayabusa missions used it to visit asteroids, collect samples, and return to Earth. Ion propulsion works. The limitation is thrust. An ion drive produces extremely low force measured in millinewtons. The force exerted by a piece of paper resting on your palm is roughly comparable. Over months and years, in the frictionless environment of space, that force accumulates into meaningful velocity. But for crewed missions, where you need to reach a destination within biological and psychological limits, the slow acceleration of ion propulsion is a real constraint. Ion drives also require substantial electrical power. In the inner solar system, solar panels can provide it. In the outer solar system, where sunlight drops with the square of distance from the sun, solar panels become insufficient. At Jupiter's distance, solar intensity is about 4% of what it is at Earth. At Saturn's, about 1%. Running useful ion propulsion beyond Mars requires nuclear power sources, and at that point, the nuclear power plant mass starts competing with the propellant savings. Ion propulsion is a genuine tool for specific missions. Robotic probes. Cargo missions, where time isn't the binding constraint. Gravity assists trajectories where chemical propulsion would struggle. For crewed missions requiring meaningful speed within human timeframes, it helps at the margins. It doesn't change which destinations are accessible. It's worth naming because it's real and proven, and because any honest account of where propulsion technology currently sits has to include the things that actually work. Chemical rockets work. Ion drives work. Nuclear thermal was proven on the ground and is being moved toward flight testing. Everything above that is unbuilt. Nuclear pulse propulsion is the most powerful propulsion concept ever, seriously studied by credentialed physicists and engineers, using real calculations, real scale models, and real engineering drawings. It was not a thought experiment. It was a program. Project Orion ran from 1958 to 1965, led initially by Ted Taylor and Freeman Dyson, two of the most respected physicists of their generation. The concept is what it sounds like. You detonate nuclear devices behind the spacecraft. Each detonation drives against a massive pusher plate connected to the ship through a system of shock absorbers. The shock absorbers smooth out the repeated impulses into something the crew and the structure can survive. Scale models were physically built and tested using conventional chemical explosives to validate the pusher plate mechanism. The mechanical principle worked. The physics of using nuclear detonations for propulsion was sound. Dyson worked out what a large Orion vessel burning fission devices could achieve. The answer was staggering. A ship of that type could reach Mars in weeks rather than months. Jupiter's moons in weeks. Saturn in a matter of months. Pluto in roughly a year. The entire solar system, from the asteroid belt to the Kuiper belt, from Jupiter's radiation-soaked moons to the cold outer reaches beyond Neptune, all of it becomes accessible on timescales measured in months to a few years. That's not the same map. That's a completely different universe of possibility. The interstellar variants of Orion, using thermonuclear devices rather than fission bombs, Dyson calculated could accelerate a massive ship large enough to carry a small community to several percent of the speed of light. At 3% of light speed, Proxima Centauri is a voyage of roughly 140 years, within the range of a generation ship. Not a single lifetime mission, but not the 70,000 years you get with Voyager's speed. Project Orion lost its footing after the Partial Test Ban Treaty of 1963, which prohibited nuclear weapons detonations in space, and the program was shut down by 1965. The treaty was the right policy for the world at the time. It also terminated the most capable space propulsion program ever seriously engineered. The physics hasn't changed. A nuclear pulse spacecraft of the type Orion was designing would still work today. It just can't be built under current international law. So, what comes after nuclear pulse, if you're asking about the ceiling rather than the near term? The answer is fusion propulsion. Fusion is the process that powers the sun and every star in the galaxy. Light atomic nuclei isotopes of hydrogen, specifically deuterium, tritium, and helium, 3 are compressed and heated to the point where they fuse together. The result is heavier nuclei and an enormous release of energy. The energy density of fusion reactions is millions of times greater than chemical combustion. It is also substantially greater than fission on a per-mass basis. A fusion rocket operating at high efficiency could achieve exhaust velocities of several % of the speed of light. At those velocities, the entire solar system compresses to the manageable. Mars in days rather than months. Jupiter in weeks. The outer planets in months. The Kuiper Belt and the heliopause, the outer boundary of the Sun's domain at roughly 100 astronomical units, reachable within years. And the nearest stars begin to come into view as destinations rather than impossibilities. Not comfortably, not quickly by any ordinary standard, but within a human lifetime, depending on what fraction of light speed a fusion drive can achieve. The challenge is that we haven't built a working fusion reactor. Not yet. Fusion research has been pursued with serious funding since the 1950s. The progress has been genuine, even when the timelines proved optimistic. In December 2022, the National Ignition Facility at Lawrence Livermore National Laboratory achieved fusion ignition for the first time. The experiment produced more energy from the fusion reaction than the laser energy delivered directly to the fuel capsule. That's ignition. It had been the target of fusion research for over 6 decades. The caveat is important. The lasers consumed far more energy from the grid than the fusion reaction released. The overall energy balance remained deeply negative. But ignition proved the fundamental physics works as predicted. ITER, the International Thermonuclear Experimental Reactor, under construction in southern France, a collaboration between 35 countries, is designed to demonstrate sustained fusion output at 10 times the input power. If ITER achieves its design goals, it establishes that fusion power is achievable at the scale needed for energy generation. The step from fusion power to fusion propulsion is enormous, but it's a direction, not a wall. Private fusion is also accelerating. Commonwealth Fusion Systems is building a compact tokamak using high-temperature superconducting magnets. Helion Energy is pursuing a pulsed approach and has secured contracts contingent on delivering net electricity. TAE Technologies and others are working on alternative confinement concepts. Whether any of these timelines deliver what they promise is genuinely uncertain. Fusion has a long history of timeline slippage. But the field is better funded, working with better materials, and operating with better diagnostics than at any previous point in its history. If fusion propulsion arrives within this century, a plausible, if not certain, prospect, the ceiling on human exploration shifts from the inner solar system to the entire solar system and the very edge of interstellar space. That's the second complete redrawing of the map. But it still doesn't get you to the stars within a human lifetime. Not quite. For that, you need the next tier. There's a thread running through the history of propulsion that's worth pulling on, because it reveals something about how the ceiling moves. Every propulsion tier in history has been dismissed before it worked. Chemical rockets were dismissed as impractical for space travel well into the 1920s. Konstantin Tsiolkovsky worked out the mathematics of rocket propulsion in the 1890s, but the engineering was considered fantastical. Robert Goddard, who launched the first liquid-fueled rocket in 1926, was publicly ridiculed by the New York Times, which ran an editorial dismissing the idea that a rocket could work in the vacuum of space, misunderstanding basic physics. The Times printed a correction on July 17, 1969, the day after Apollo 11 lifted off for the moon. Nuclear thermal propulsion was studied and tested and worked. It was cancelled. It's being revived. The Draco flight demonstration aims to validate a nuclear thermal engine in actual space conditions before the end of this decade. If that test succeeds, nuclear thermal propulsion will have a flight-proven pedigree for the first time, and the conversations about crewed nuclear thermal missions will shift from theoretical to engineering. Fusion propulsion doesn't exist yet, but fusion ignition has been achieved. ITER is under construction. Private fusion companies are reporting results that, if they hold, compress the timeline considerably. The direction is real, even when the timeline is uncertain. Antimatter propulsion doesn't exist, and has no near-term path to existence. But the physics of antimatter is understood, the production mechanisms are understood, and the constraints on what would be required to make it viable are understood precisely enough to identify what breakthroughs would change the picture. That's not the same as having no path. It's having a very long path with several hard turns. The history of technology is a history of hard turns. The internal combustion engine was a hard turn. Nuclear fission was a hard turn. Integrated circuits were a hard turn. Genetic sequencing was a hard turn. Each of them, before the turn was made, looked like a wall. Afterward, it looked like a step. The propulsion hierarchy, chemical, ion, nuclear thermal, nuclear pulse, fusion, antimatter, is a sequence of turns. We're somewhere between nuclear thermal and nuclear pulse on that sequence. Each turn we haven't made looks like a wall from where we stand. Some of them are walls. The speed of light is a wall. The others are turns. Which ones and when is genuinely unknown. But the map of which turns exist, where they lead, and what each one unlocks in terms of human reach, that map is knowable. That's the map this question is really asking about. And it looks like this. The first step is nuclear thermal propulsion, potentially available within this decade in flight-validated form. What it unlocks is safer, faster Mars missions. 3 to 4 months of transit instead of 6 to 9. Better abort options. The inner solar system becomes more manageable. The second step is nuclear pulse propulsion. Available in principle right now, blocked only by international treaty. What it unlocks is the entire solar system. Weeks to Jupiter. Months to Saturn. A year or two to the outer reaches. Crewed missions to Europa, Titan, Enceladus, the Kuiper Belt, all of it opens. The third step is fusion propulsion. Available within this century, if fusion power development delivers. What it unlocks is the solar system and the edge beyond it. The transit times that nuclear pulse makes feasible in years, fusion makes feasible in months. The heliopause and the Oort cloud become reachable. The nearest stars enter the range of generation ship architecture. The fourth step is propulsion beyond fusion, possibly antimatter, possibly something not yet described. What it unlocks is the nearest stars within a human lifetime. 42 years to Proxima Centauri. 21 years at twice the velocity. The stellar neighborhood within 10 to 20 light years becomes navigable. It isn't one number. It's 4 answers, one for each step, each one contingent on the one before it. And right now, we're somewhere between the starting point and the first step. The energy numbers for interstellar travel are worth stating plainly, because they're more clarifying than any abstract description of the challenge. To accelerate a spacecraft with a mass of 10 million metric tons, the scale of a generation-class vessel, carrying a community, decades of life support, heavy radiation shielding, and its own fuel to 10% of the speed of light, the kinetic energy required is approximately 4.5 times 10 to the power of 24 joules. That number needs context. Total global energy consumption in the year 2024 was roughly 6 times 10 to the power of 20 joules. Accelerating a crewed interstellar spacecraft to 10% of light speed requires roughly 7,500 times the total annual energy consumption of all of human civilization. All of it. Every kilowatt-hour of electricity generated globally for a full year multiplied by 7,500. That's what the physics demands. And that's just to accelerate to 10% of light speed. Decelerating at the destination requires the same energy again. The total mission energy is twice that. Roughly 15,000 years of current global energy production. Stored somehow, carried somehow, or generated in transit by an onboard reactor. This isn't meant to make interstellar travel sound impossible. It isn't impossible. The physics doesn't forbid it. It's meant to make clear why the propulsion system is everything. The only reason any of these numbers become manageable is if you have a propulsion technology with high enough energy density that a physically practical mass of fuel contains this kind of energy. Antimatter does. 1 kilogram of antimatter, annihilating with 1 kilogram of ordinary matter, releases approximately 180 quadrillion joules, close to the yield of the largest nuclear weapon ever detonated. 2 kilograms of fuel, annihilated completely, releasing the energy of a 43 megaton explosion from a mass you could hold in your hands. That's the energy density that makes interstellar travel physically tractable. And that's why antimatter propulsion, despite its production and storage problems, remains the candidate that the physics points toward when you ask what propulsion would actually have to look like. Fusion is less energy dense than antimatter, but more energy dense than fission, which is more energy dense than chemical combustion. Each step up in density is a step toward making the energy budget for interstellar travel, something a physical spacecraft can carry. The engineering challenges of each step are immense, but the direction the physics points is clear. Higher energy density is the path. And the energy densities required for human interstellar travel are real numbers that real physics produces, not infinities, not violations of natural law, just very large numbers that require very dense energy sources. The nearest star beyond our Sun is Proxima Centauri. It sits 4.24 light-years from here. In miles, that's about 25 trillion. At Voyager, one's current speed, roughly 38,000 miles per hour, crossing that distance takes approximately 70,000 years. That number isn't dramatic license. That's the math. To reach Proxima Centauri, within a single human lifetime, you need to be traveling at somewhere between 10 and 50% of the speed of light. At 10% of light speed, the trip takes 42 years. At 20%, about 21 years. At 50%, roughly 8.5. These are the velocities that make the nearest star a destination rather than an abstraction. And reaching 10% of light speed means achieving a velocity of about 18,600 miles per second. Voyager 1 travels at about 10.5 miles per second. The gap between where we are and where we need to be is a factor of roughly 1800. Fusion propulsion closes some of that gap. It doesn't close all of it. The two propulsion technologies that could theoretically reach the velocities needed for human interstellar travel within a lifetime are antimatter propulsion and laser-pushed light sails. Antimatter propulsion is the theoretical ceiling of rocket physics using known matter. When a particle of matter meets its antimatter counterpart, a proton meeting an antiproton, an electron meeting a positron, both are completely annihilated. 100% of their combined mass converts to energy. Nothing in physics is more efficient. An antimatter rocket, channeling that annihilation into directed thrust, could theoretically reach exhaust velocities approaching a significant fraction of the speed of light. The energy budget for crossing 25 trillion miles within decades is physically sufficient. The problem isn't the physics. The problem is the antimatter itself. Antimatter doesn't exist in useful quantities anywhere we can access. The universe appears to be made almost entirely of ordinary matter, a tiny asymmetry left over from the Big Bang, where matter slightly outnumbered antimatter. And everything we see today is the survivor. Every particle of antimatter we've ever studied was manufactured in particle accelerators produced by colliding ordinary matter at extremely high energies, and then isolated using magnetic traps before it could touch anything and annihilate. The total amount of antimatter produced by all particle accelerators in human history, accumulated across decades of operation at facilities around the world, including CERN, is measured in nanograms, billionths of a gram. A crude interstellar mission would require kilograms. The energy cost to manufacture a single gram of antihydrogen with current accelerator technology would exceed what the world produces in a year. The time required to accumulate kilogram quantities at current production rates is not thousands of years. It's millions. And that's before confronting the storage problem. Antimatter cannot contact any ordinary matter without instantaneous annihilation. Storing kilograms of it requires magnetic confinement systems of extraordinary precision, sustained without a single failure for the entire duration of the mission. A containment failure doesn't mean losing your propellant. It means the propellant explodes with an energy release that makes thermonuclear weapons look modest. 1 kilogram of antimatter annihilating releases energy equivalent to roughly 43 megatons. Antimatter propulsion is not an engineering program approaching feasibility. It's a description of what perfect rocket propulsion would look like if the universe were more cooperative. It points at a ceiling. It doesn't hand you a ladder. Laser-pushed light sails are the third candidate for interstellar velocity. The concept uses photon pressure. Light exerts a tiny force on any surface it strikes. A large reflective sail intercepts photons from a powerful ground-based laser, and the momentum transfer pushes the spacecraft forward. The crucial advantage is that the energy source stays behind. The spacecraft carries no propellant, no reactor, just the sail and whatever payload it carries. Without propellant mass, the spacecraft can be made extraordinarily light, and a lighter spacecraft accelerates faster with a given laser power. Breakthrough Starshot. Announced in 2016 and backed by significant private funding, proposed a laser array, delivering 100 gigawatts onto a gram-scale sail of roughly several meters. The calculations showed that a sail massing only a few grams could be accelerated to approximately 20% of the speed of light. The trip to Proxima Centauri at that velocity takes about 20 years. The engineering challenges are serious. 100 gigawatts delivered onto a moving target requires thousands of laser sources synchronized with extraordinary precision. The sail material needs to reflect, essentially, all incident laser light. Even a fraction of a percent absorbed would vaporize it during acceleration. Nanometer-scale sail fabrication doesn't exist yet. Interstellar dust particles, striking at 20% of light speed, carry enormous impact energy relative to the sail's mass. And then, the constraint that makes Breakthrough Starshot irrelevant to the question of human travel. It's designed for a probe massing a few grams, not a person. The mass of a life support system, a crew habitat, food, water, shielding, and navigation equipment is many orders of magnitude larger than a few grams. Scaling the laser power to accelerate a crewed spacecraft to the same velocity would require an installation not the size of a city block, but the size of a continent. The physics of laser light sails, as currently conceived, doesn't scale to crewed missions. It might work for robotic precursors. It does not represent a path to sending people. So the honest summary of where interstellar propulsion stands is this. We have no technology that can currently accelerate a human-carrying spacecraft to interstellar velocities. We have promising research directions, fusion, and longer-term possibilities, but nothing engineered, nothing tested, nothing close to operational. The nearest star is 25 trillion miles away. The propulsion gap between where we are and where we need to be is measured in specific impulse terms, a factor of thousands. That's not a small gap to close. That's a civilizational project. It's worth spending a moment on the deceleration problem specifically, because it almost never receives the attention the acceleration problem gets, and it's equally hard. Popular discussions of interstellar travel focus almost entirely on how you get up to speed, the propulsion needed, the fuel mass, the exhaust velocity. These are the right things to focus on for the outbound leg. But arriving at another star at 10% of the speed of light with no way to slow down isn't a mission. It's a flyby. At 18,600 miles per second, you'd traverse the entire Alpha Centauri system in a matter of hours. You'd gather data during that brief encounter and continue on into deep space, unable to return, unable to stop. Eventually, just another object moving through interstellar space with no remaining purpose. For a crewed mission that means something that actually establishes a human presence in another stellar system, you have to stop. And stopping requires the same order of magnitude of energy as accelerating. Which means you either carry twice the propellant, dramatically worsening the mass ratio and the energy requirements for the whole mission, or you use something at the destination to slow you down. Several proposals exist. Magnetic braking against the interstellar medium. As a spacecraft moves through interstellar space, it encounters a thin plasma of ionized hydrogen and helium. A large superconducting loop deployed ahead of the spacecraft would create a magnetic field that interacts with this plasma, creating drag. Over years, this drag decelerates the spacecraft. The technique is called a magnetic sail, or mag sail. It works best at relatively low fractions of light speed, where the interstellar medium is dense enough relative to the spacecraft's velocity to provide meaningful braking force. At high velocities, the interaction becomes more complex, and the braking force may not be sufficient on its own. Photon, braking against the destination star. The same light sail used for laser acceleration can be reoriented to catch photons from the destination star, using starlight to slow down. As the spacecraft approaches, the stellar radiation pressure pushes against the sail from ahead rather than behind. The deceleration is gradual. It begins when the star's photon pressure becomes significant relative to the spacecraft's momentum. For a star like Proxima Centauri, which is much dimmer than our Sun, the braking force from stellar radiation is limited, and the process takes years. But it doesn't require carrying additional propellant. The energy comes from the star itself. A two-stage mission architecture. The propulsion system used for acceleration is also used for deceleration. The spacecraft flips orientation at the halfway point and fires engines retrograde, slowing down continuously from the midpoint to arrival. This requires carrying all the deceleration propellant from the start. It doubles the propellant mass requirement, which makes the mass ratio worse, which requires even more propellant to accelerate the additional deceleration propellant. The rocket equation spirals badly, but it's the most self-contained approach. No dependence on stellar wind strength. No requirement for precise sail orientation at high velocity. Just thrust, continuously applied. Each approach has engineering trade-offs. None of them have been tested beyond theoretical analysis and small-scale laboratory experiments. The deceleration problem is as hard as the acceleration problem, and any honest account of what it would take to send humans to another star has to include both halves. The interstellar medium deserves more attention than it usually gets in discussions of deep space travel. Because when people imagine crossing the distance between stars, they imagine crossing emptiness. And interstellar space is empty, in the sense that it contains far fewer atoms per cubic meter than any vacuum humans have ever created on Earth. But it isn't nothing. The interstellar medium is a thin plasma of gas and dust, mostly hydrogen and helium, with traces of heavier elements and complex molecules in denser regions. The average density in our local neighborhood is roughly 1 atom per cubic centimeter. 1 atom per cubic centimeter sounds like nothing. At 10% of light speed, it isn't. At 10% of light speed, a spacecraft is moving at about 18,600 miles per second. Each atom of interstellar hydrogen that the spacecraft encounters is, from the spacecraft's perspective, hitting it at that velocity. The kinetic energy of each collision is enormous relative to the mass of a hydrogen atom. Individual atoms don't damage a spacecraft hull. But over 4 decades of travel, the cumulative erosion of the leading edge of the spacecraft from interstellar particle impacts becomes a real engineering concern. And it isn't just erosion. The electromagnetic interaction between a high-velocity spacecraft and the interstellar medium creates effects that have to be modeled and accounted for. There's also the dust. Interstellar space contains grains of silicate and carbon compounds, microscopic particles ranging from nanometers to fractions of a millimeter across. At 10% of light speed, a 1 microgram dust grain hitting the front of a spacecraft delivers an impact energy comparable to a small explosive. Not catastrophic by itself. But the density of dust grains isn't uniform. The interstellar medium has denser and thinner regions. A spacecraft crossing 4 light-years doesn't know in advance what density profile it will encounter. The leading-edge shielding design has to account for the worst plausible case, which adds mass, which increases the energy cost of acceleration, which feeds back into the propulsion requirements. There's also the radiation environment of interstellar space itself, separate from the question of galactic cosmic rays passing through the crew habitat. A spacecraft hull interacting with interstellar particles generates secondary radiation. Fast-moving protons hitting the hull material create showers of secondary particles, neutrons, gamma rays, pions that penetrate further into the structure than the original particle would have. The shielding problem for an interstellar spacecraft is not the same as the shielding problem for a spacecraft in the solar system. The energy regime is different. The particle types are different. The duration is different. The engineering solutions that work for a Mars transit, already challenging, need to be rethought almost from scratch for an interstellar mission. None of this makes interstellar travel impossible. It makes it harder than the simple propulsion calculation suggests. And it means that the civilizational investment required to send people to another star is not just a matter of building a more powerful engine. It's a matter of solving a comprehensive system of interconnected engineering problems, each of which is individually formidable and none of which have obvious near-term solutions. The honest version of "we could reach the nearest star" is, we could reach the nearest star if we had fusion or antimatter propulsion, if we had shielding that could protect a crew against decades of full galactic cosmic ray exposure, plus the secondary radiation generated by interstellar particle impacts, if we had life support that could function reliably for 40 or more years with no resupply, if we had a deceleration solution that doesn't require carrying twice the propellant load, if we had solved the psychological architecture of a multi-decade isolated mission, and if we had the institutional commitment to sustain a program across the timescales required to develop all of the above, each of those ifs is a serious open engineering problem. None of them are violations of physics. All of them are solvable in principle. None of them are solved today. That's the honest state of the question. But propulsion isn't the only wall between us and the stars. Even if you solve the propulsion problem entirely, even if you hand a crew a ship capable of traveling at 10% of light speed, you haven't solved the mission. You've solved one variable in an equation with several. The second variable is time. Not travel time, in the abstract. Time as something the human body has to survive. A 42-year transit to Proxima Centauri at 10% of light speed means 42 years in the deep space environment. In deep space, there is no protective magnetic field. The sun's protective bubble, the heliosphere, ends at the heliopause, roughly 100 astronomical units from the sun. Beyond that boundary, which Voyager 1 crossed in 2012, the full galactic cosmic ray flux arrives unattenuated from all directions. Galactic cosmic rays are high-energy particles accelerated by supernova remnants, neutron star collisions, and other violent events throughout the galaxy. They stream through interstellar space continuously. They pass through spacecraft walls. They pass through human tissue. They ionize molecules inside cells, including DNA. The longer a crew is exposed, the higher the cumulative damage. Current shielding approaches water walls, polyethylene. Hydrogen-rich materials absorb lower energy particles, but do little against the highest energy galactic cosmic rays. Those particles are moving so fast that the shielding material itself becomes a source of secondary radiation when hit. 42 years of that exposure represents a radiation dose that current biology simply cannot survive in any functional sense. Cancer rates across a crew exposed to the full galactic cosmic ray flux for 4 decades would be essentially universal. This isn't a technology gap, it's a biology gap. And solving it requires either radical improvements in shielding, which means mass, which means propulsion requirements increase, or changes to human biology itself. The biology question is where the answer to the title question becomes genuinely open-ended. Because the human body that exists today is not necessarily the human body that eventually travels to the stars. Radiation resistance is a biological trait. Some organisms, tardigrades, Deinococcus radiodurans, certain extremophile bacteria tolerate radiation doses that would be instantly lethal to humans because their DNA repair mechanisms operate far more efficiently. Gene therapy has already demonstrated the ability to alter specific genetic traits in living organisms. CRISPR allows targeted editing of DNA with precision that didn't exist 15 years ago. It's plausible, not certain, but plausible that future space travelers carry genetic modifications that improve radiation resistance, reduce bone density loss in microgravity, or improve cardiovascular resilience in environments without normal gravity. This is uncomfortable territory for some people. It sits at the boundary of biology and identity. But it's also the honest answer to the question of what furthest humans could ever travel actually requires at the biological level. The entity that eventually reaches the nearest stars may not be biologically identical to the species that built the ship. The third variable is the deceleration problem. This one gets far less attention than it deserves. You've accelerated a crewed spacecraft to 10% of light speed. You've sustained the crew through 40 years of deep space transit. You're approaching Proxima Centauri. Now you need to stop. Decelerating from 10% of light speed requires exactly as much energy as accelerating to it. You need to fire engines in the reverse direction for roughly the same duration as the initial acceleration phase, which means carrying or finding at the destination as much propellant as you burn to get there. If you carry it from Earth, you've doubled the propellant mass, which requires more energy to accelerate, which requires more propellant, and the rocket equation spirals upward in a way that rapidly makes the mission mass impractical. Some proposals involve using the destination star's own radiation pressure to brake against deploying the sail in reverse orientation to catch the target star's photons. The deceleration is slower than laser-assisted acceleration, but it's physically possible. Others propose a magnetic sail, interacting with the interstellar medium, using the thin plasma of hydrogen atoms between the stars as a brake. This also works in principle. In practice, neither has been tested. Neither is close to being testable with current technology. And there's the fourth variable, the human mind. The psychology of a 42-year mission is a genuinely unknown territory. No human being has ever been more than about 250,000 miles from Earth. The record for continuous time in space is held by Russian cosmonaut Valery Polyakov, who spent 437 days aboard the Mir space station from 1994 to 1995. That's 14 months. The psychological research on extreme long-duration isolation from Antarctic winter overcruise, submarine missions, isolation studies has identified patterns that appear consistently. The third quarter phenomenon. Mood and performance reliably decline during the third quarter of any isolated mission, regardless of its total length. Communication delay matters enormously. Even delays of hours alter psychological landscape. At 1 light year from Earth, messages take 1 year to arrive and a year to return. At 2 light years, 2 years each way. By the midpoint of a trip to Proxima Centauri, Mission Control receives your message in 2 years and sends a response that arrives 2 years after that. Whatever was urgent isn't anymore. The crew is not just physically isolated. It's temporally isolated. Cut off, not just by distance, but by the speed of light itself. Social dynamics that seem manageable in training simulations would play out over decades rather than months. In a vessel with no ability to leave and no outside mediator reachable within any practical time frame. What happens to a crew's governance structure as the original commander ages into their 70s? What happens when fundamental disagreements arise that cannot be resolved and cannot be appealed to anyone reachable? These aren't small questions. They're questions that have never had to be answered because no mission has ever placed them in front of real human beings in a real situation with real consequences. The generation ship concept sidesteps some of the individual psychology problem by acknowledging the duration honestly. If a voyage takes 100 years, you don't pretend one crew survives it. You build a ship large enough for a small community. People live, work, reproduce, and age aboard it. The children born on the ship know no other home. Their children know no other home. Eventually, generations removed from the people who launched it, the ship arrives. The concept works in principle. It also raises questions that are more ethical than engineering. The first generation chose the mission. The second generation was born into it. By the time the ship arrives, the people aboard may have no meaningful connection to the civilization that sent them, or to the mission parameters that were set before any of them were born. What authority does a 200-year-old mission brief have over people who never signed it? These questions don't have clean answers. They're the questions a civilization would have to resolve before committing to a generation ship. Not engineering questions, but fundamental questions about consent, identity, and what we owe to people who don't exist yet. Suspended animation offers a different approach. If crew members could be kept in a state of reduced biological activity, aging little, or not at all during the transit, the social and psychological problems of a multi-generational voyage collapse back to a single crew mission. The science is genuine at its edges. Therapeutic hypothermia is used in medicine to slow metabolism during cardiac surgery. Some organisms survive extreme metabolic arrest indefinitely. Tardigrades can desiccate almost completely and revive decades later. The gap between those biological facts and human suspended animation, lasting decades, is enormous. Mammalian metabolism doesn't pause the way simpler organisms can. The the cellular mechanisms are different. Whether that gap is bridgeable with future biology is an open question. It isn't close to being answered. But it's an open question, not a closed one. The question of human biology in deep space gets treated as a fixed constraint when it's actually a moving one. And understanding how it moves changes the long-term answer to how far humans could travel. The human body in its current form did not evolve for space. It evolved for a specific gravitational field, Earth's 1G over roughly 300,000 years. It evolved under a specific radiation environment, protected by the magnetosphere and atmosphere. It evolved with a specific circadian rhythm driven by a 24-hour day. It evolved to experience a specific range of temperatures, atmospheric pressures, and chemical environments. In deep space, almost none of those conditions hold. The gravity is zero or near zero. The radiation environment includes galactic cosmic rays and solar particle events unattenuated by any magnetosphere. The circadian rhythm loses its anchor when there's no natural day-night cycle. The temperature and pressure are maintained only by engineering, not by planetary atmosphere. The physiological responses to these conditions have been documented by decades of research on International Space Station crews. Bone density loss begins within days of entering microgravity and continues throughout the mission. Cardiovascular deconditioning begins within weeks. Muscle mass declines despite exercise countermeasures. Fluid shifts from the lower body toward the head, elevate intracranial pressure in ways that affect vision and cognitive function. The immune system shows changes that aren't fully understood. Gene expression profiles measurably shift. Gut microbiome composition changes. These are the effects documented after missions of months. The effects of years or decades are extrapolated from shorter missions and from biological models. The extrapolations are uncertain. It's possible that some effects plateau, that the body reaches a new equilibrium in microgravity and stops deteriorating further. It's also possible that some effects are cumulative in ways that shorter missions don't reveal. We don't know. And not knowing is itself part of why long-duration spaceflight remains a research program rather than a solved problem. The countermeasures research is real and is producing results. Resistance exercise in microgravity has reduced but not eliminated bone density loss. Lower body negative pressure devices that pull fluid back toward the lower body have shown promise in mitigating the intracranial pressure issue. Pharmacological bone density support is being investigated. Targeted nutrition protocols are being refined. Each countermeasure chips away at one part of the problem. None of them together have been shown to fully preserve normal human physiology for mission durations. Beyond about 14 months, the current record for continuous spaceflight. The gap between 14 months and 42 years is enormous. It's possible that the gap closes as countermeasure technology improves. It's possible that it doesn't close with countermeasures alone and requires biological modification. The genetics of radiation resistance is a real field of study. Certain organisms have radiation repair mechanisms that make them effectively immune to radiation doses that would be lethal to humans. The genes involved have been identified. Whether they can be introduced into human biology in a functional way, whether the relevant proteins can be expressed in human cells in a way that protects without disrupting other biological functions is an open research question. Gene therapy has already demonstrated in clinical settings that specific genetic modifications to human cells are achievable. It has not demonstrated whole organism genetic modification for radiation resistance in humans. The path exists in principle. Whether it's traversable is what decades of future research will determine. The point isn't that human biology will definitely be modified for interstellar travel. The point is that the biological ceiling, what the human body can survive in deep space, is not a fixed number. It's a research target. And research targets move. There's also the question of what you're actually trying to achieve when you go. The answer shapes the architecture more than people realize. A crude flyby of Proxima Centauri arriving at speed, conducting observations over hours or days, then continuing into space with no ability to stop, is vastly easier than a crude orbital mission. You need roughly half the total propellant. You don't need deceleration propellant. The transit time is the same, but the mass and energy requirements for the ship are dramatically lower. Of course, a flyby gives you hours of close observation of a star system after 40 years of travel. That's not nothing. It's still the first close look humans have ever had at another stellar system. But it's not a permanent presence. It's not a landing. It's a brief, fast encounter. An orbital mission requires deceleration. You arrive at speed and shed velocity using propulsion, using the target star's radiation pressure, using a magnetic sail interacting with the stellar wind, or some combination. You spend time in the system. You study the planets up close. If there's a habitable planet, you might enter orbit around it. If the habitability assessment is favorable, future missions could build toward a landing. A landing mission requires even more. You need to carry or manufacture descent propellant. You need surface infrastructure. If anyone is ever to come back, which is the hardest part of any planetary mission, you need ascent propellant manufactured on the surface from local resources, assuming local resources exist and can be processed. Each level of ambition approximately doubles or more the energy and engineering requirements. A flyby, an orbital mission, a surface landing, a return, a permanent outpost. The question, how far could humans ever travel, doesn't have a single answer, because travel has different meanings depending on which of those levels you intend. The furthest a human has ever physically traveled is the Moon, 250,000 miles, with a landing and a return. The furthest a human probe has ever physically traveled is Voyager 1. Currently, about 165 astronomical units from the Sun, but it's a flyby that never stopped and never returns. The furthest a human crew has ever been from Earth is about 250,000 miles. The furthest we could plausibly go with a flyby architecture, given fusion propulsion, is the nearest stars. No landing, no return. Just the transit and the data. The furthest we could go with a full mission architecture orbit, land, return, is currently Mars. And Mars hasn't been done yet. Each of those answers is technically correct. They're answering slightly different versions of the question. So the honest answer isn't a single distance. It's a flyby of the nearest stars, or a landing on Mars, depending on what you mean by getting there. And both of those are still ahead of us. The destinations the solar system actually offers, the ones that exist between Mars and the heliopause, are some of the most scientifically extraordinary places ever studied by any spacecraft. And virtually none of them have been seen by human eyes, even from orbit. Jupiter's moon Europa has a global ocean of liquid water beneath an ice shell. The ocean is real. The Galileo spacecraft detected it through magnetic field measurements in the 1990s, and subsequent missions have confirmed its existence. The shell is estimated to be somewhere between 10 and 30 miles thick. Beneath it, the ocean may be 60 miles deep. That ocean contains more liquid water than all of Earth's oceans combined. It's kept liquid, not by proximity to the Sun. Jupiter is 5 times further from the Sun than Earth, and Europa's surface temperature is around negative 260 degrees Fahrenheit, but by tidal heating. Jupiter's gravity is enormous, and as Europa orbits, the varying gravitational pull continuously flexes and compresses the Moon's interior. That flexing generates heat. The heat keeps the ocean liquid, and where there's liquid water, chemical energy, and time, life has arisen on Earth. Whether it has arisen on Europa is one of the most important unanswered questions in science. Europa Clipper, launched by NASA in October 2024, is currently en route to Jupiter to perform dozens of close flybys of Europa, characterizing the ice shell, looking for plume activity, and assessing the ocean's chemistry. The data it returns will tell us how seriously to take Europa as an astrobiology target. And a crewed mission to Europa, once fusion propulsion makes the transit time reasonable, would place human scientists in direct proximity to what may be the most consequential scientific destination in the solar system. Enceladus, the small moon of Saturn, has already proven itself. The Cassini spacecraft, orbiting Saturn from 2004 through 2017, flew directly through geysers of water erupting from beneath Enceladus's icy south polar region. The geysers contain water vapor, ice, particles, salts, and organic compounds. They originate from a subsurface ocean. Cassini detected molecular hydrogen in the plumes, which is significant because molecular hydrogen in the presence of liquid water and minerals is a signature of hydrothermal activity, the same kind of chemical energy source that supports ecosystems on Earth's ocean floor, independent of sunlight. Enceladus is actively venting its interior into space. You could, in principle, fly a spacecraft through those plumes and collect samples of a subsurface ocean without ever having to land or drill through ice. The scientific case for a crewed mission to Enceladus, once propulsion makes it accessible, is not simply about exploration for its own sake. It's about answering whether life in the universe is a rare accident of Earth's particular circumstances, or a common outcome wherever the right conditions exist. Titan, Saturn's largest moon, offers a different kind of extraordinary. Its atmosphere is thicker than Earth's, primarily nitrogen, with significant methane, at a surface pressure about 1.5 times Earth's sea level. The surface temperature is around negative 290 degrees Fahrenheit, cold enough that methane exists as a liquid, forming lakes, rivers, and seas in the polar regions. The Dragonfly mission, a NASA rotorcraft lander approved for development, is designed to fly between surface sites on Titan, studying its complex organic chemistry. Dragonfly is expected to launch in 2028 and arrive at Titan in the mid-2030s. Titan's thick atmosphere means that a human on the surface would need breathing equipment, but not a pressure suit. The atmospheric pressure is livable. The cold is the challenge. But, from a life support engineering standpoint, Titan is far more forgiving than the vacuum of space or the thin, toxic atmosphere of Mars. Ganymede, the largest moon in the solar system, larger than the planet. Mercury has its own intrinsic magnetic field. the only moon anywhere known to have one. Callisto, in a relatively stable orbit outside the worst of Jupiter's radiation belts, is considered a potential base of operations for exploring the Jovian system. These are the destinations that nuclear pulse propulsion opens and fusion propulsion makes routine. They're not consolation prizes for failing to reach the stars. They're some of the most extraordinary places in the known universe. And they're within the solar system, which is still technically our backyard. The stars in the night sky are not equally distributed in distance. Some of the stars you can see tonight are relatively close. Some are hundreds or thousands of light years away. And the distinction matters enormously when you're thinking about where humans could realistically aim. The stellar neighborhood, within about 15 light years of the Sun, contains roughly 30 known star systems. Most of them are red dwarfs, small, dim, long-lived stars that make up the vast majority of stars in the galaxy. Red dwarfs are interesting scientifically. They're also the most problematic hosts for habitable planets because their habitable zones are close enough to the star that planets there are likely tidally locked. And because red dwarfs produce powerful flares at higher frequency than our Sun, the Sun-like stars G-type and slightly cooler K-type main sequence stars are less common in the nearby neighborhood, but more promising as hosts for Earth-like planets. Tau Ceti, at 11.9 light-years, is a G-type star moderately similar to our Sun. It has candidate planets, including possibly one or two in the habitable zone. The system has substantially more debris disk material than our solar system, which raises questions about impact rates. But it's a real candidate. Alpha Centauri A, at 4.37 light-years, is a G-type star, essentially the same size as our Sun. Alpha Centauri B, its binary companion at the same distance, is a K-type star, slightly smaller and cooler. Whether habitable planets orbit either of them is unresolved. The binary nature of the system means orbital dynamics are complicated. Stable planetary orbits exist in the right zones, but require specific conditions to form and remain stable. Sirius, the brightest star in the night sky from Earth, sits at 8.6 light-years. It's a white main sequence star roughly twice the mass of our Sun, much hotter, burning brighter. It has a white dwarf companion Sirius B, the remnant of a star that has already exhausted its nuclear fuel. The prospects for habitable planets around Sirius are considered poor. The target-rich environment for interstellar human exploration is not, as it turns out, particularly close. Within the first 10 light-years, the candidates are limited. Within 20 light-years, the picture expands. At 20 light-years, you have access to dozens of stellar systems, several of them with Sun-like hosts, and candidate planets in habitable zones detected by current instruments. But 20 light-years, at 10% of light speed, is a 200-year voyage. No single crew survives that. You need a generation ship, which means the choice of propulsion velocity matters not just for transit time, but for what kind of mission architecture becomes necessary. At 10% of light speed, Proxima Centauri, in 42 years, barely within a single long career. Alpha Centauri, in 43.7 years. Similarly, Tau Ceti, in 119 years, requiring a generation ship, at 20% of light speed. Proxima Centauri, in about 21 years. Tau Ceti, in about 60 years. Sirius, in about 43 years. At 20% of light speed, the entire stellar neighborhood within 10 light-years becomes accessible within a single human career. At 30%, most stars within 10 light-years become single-career missions. At 50%, the stars within 25 light-years come within single-career range. These are the thresholds that define what reach actually means for interstellar exploration. And they clarify why the velocity achieved by the propulsion system matters so enormously. Not just for whether you arrive in 40 years or 100, but for whether you need a generation ship at all. Whether the people who launch are the people who arrive. Whether the mission is something individuals can commit to knowing they'll see it through. The difference between 20 and 50% of light speed, both of which require propulsion technology that doesn't exist, is the difference between a mission that requires generational sacrifice and a mission that requires extraordinary personal commitment. Both are profound. They're not the same thing. One of the most underrated facts about the nearest stellar neighborhood is how much we don't know about it. We've detected planets around a handful of the nearest stars. We don't know the full inventory. The detection methods we use, radial velocity, transit photometry, direct imaging, each have biases. Radial velocity is most sensitive to massive planets orbiting close to their stars. Transit photometry requires the planet's orbital plane to be aligned nearly edge-on relative to our line of sight, which only happens for a fraction of systems. Direct imaging is extremely challenging for Earth-scale planets at the distances of nearby stars. The planet we know most about around Proxima Centauri, Proxima Centauri b, was detected via radial velocity. A second candidate planet and a possible third have been reported. None have been confirmed with certainty. Around Alpha Centauri, candidate detections have been reported and subsequently disputed. The system's binary nature makes planet detection harder because the gravitational influence of both stars creates noise in the radial velocity signal. What we know about the stellar neighborhood within 10 light-years is almost certainly incomplete. There may be Earth-mass planets around nearby stars that current instruments can't detect. There may also be no habitable worlds within 30 or 40 light-years. We don't know. And that uncertainty isn't a minor detail in the question of how far humans should try to go. If there's a confirmed Earth-like planet with biosignatures around a star 8 light-years away, the case for pushing the propulsion frontier as hard as possible becomes concrete. It changes from abstract ambition to specific destination. If the nearest hospitable environment turns out to be 30 or 40 light-years away, the mission architecture changes significantly. 30 light-years at 20% of light speed is 150 years. No individual crew completes that. The institutional commitment required isn't a single generation's project. It's a decision that shapes what civilizations build and fund across centuries. This is why the next generation of space telescopes matters enormously for the question this script is asking. The Habitable Worlds Observatory, a proposed NASA flagship telescope with a primary mirror large enough to directly image Earth-scale planets around nearby sun-like stars and perform spectroscopy on their atmospheres, would change what we know about the nearest stellar neighborhood fundamentally. Spectroscopy of a planet's atmosphere from 30 light-years away can detect the presence of oxygen, methane, water vapor, ozone, and other molecules that on Earth are strongly associated with biological activity. Not proof of life, but evidence that makes the question impossible to ignore. If that telescope reveals biosignatures around a star within 20 light-years, the conversation about human interstellar travel transforms overnight. The question stops being abstract. It becomes, do we go? And if we go, how? That's the moment when all the propulsion research, all the biology research, all the institutional commitment question gets put on the table simultaneously, and the civilization has to decide what kind of civilization it is. We're not there yet, but we could be, within this century, with the right telescopes. The answer to how far humans could ever travel in space depends partly on what we find before we decide to go. So, what does the full picture look like? What is the actual answer to how far humans could ever travel? It looks like tiers. Each tier is defined by a propulsion technology, and each technology unlocks a completely different range. With chemical propulsion, what we have now, the ceiling, is Mars. 34 million miles at closest approach. The Moon is 250,000 miles. We've done that. Mars is the door we're standing in front of. With nuclear thermal propulsion proven on the ground, being moved toward flight testing, the ceiling rises, but the map doesn't fundamentally change. Nuclear thermal gets you to Mars faster and more safely. It doesn't get you to Jupiter. Not in any crude mission architecture that works within human biology and psychology. With nuclear pulse propulsion, the physics works, the politics stopped it, the entire solar system opens. Weeks to Mars. Weeks to Jupiter. Months to Saturn. A year or two to Pluto and the Kuiper Belt. The heliopause, the edge of the sun's bubble in interstellar space, at roughly 100 astronomical units becomes reachable. Crude missions to the moons of Jupiter and Saturn become feasible on career timescales. This is where human exploration expands from the inner solar system to the whole of it. If you give the political problem back to the engineers, nuclear pulse is where the solar system's ceiling lifts. With fusion propulsion, the next tier after pulse, still unbuilt but actively researched, the ceiling lifts further again. Fusion exhaust velocities could compress the solar system to something navigable in months rather than years. And fusion begins to make interstellar distances not impossible, just very long. At a few percent of light speed plausible for an advanced fusion drive, Proxima Centauri becomes a journey of centuries. Still beyond a single lifetime. But a generation ship becomes conceivable. And for the first time, the stars aren't just philosophy. They're engineering. With antimatter propulsion, if the production problem is ever solved, which current physics offers no near-term path to doing, the nearest stars become reachable within a human lifetime. 42 years to Proxima Centauri at 10% of light speed. 21 years at 20%. The stars within 15 to 20 light years, dozens of stellar systems, several with candidate planets, become accessible on single-mission timescales. This is the theoretical ceiling of known rocket physics. Beyond antimatter, you're in territory that requires either physics we don't have yet or fundamental rethinking of what propulsion means. The hard wall, the one that doesn't move regardless of technology, is the speed of light. Nothing with mass can reach it. This isn't a technological limitation. It's a structural feature of space-time. Einstein's equations don't leave wiggle room. As you approach light speed, the energy required to accelerate further increases without bound. The last percent of the gap between you and light speed costs more energy than everything before it combined. The universe physically prevents anything with mass from reaching the speed of light, which means, even at the most optimistic end of the propulsion spectrum, travel to stars beyond a few tens of light years takes decades to centuries. The galaxy, 100,000 light-years across, 200 to 400 billion stars, is not a place any individual human travels across. It's a place a civilization spreads across, slowly, over millions of years, if it survives long enough and solves enough problems. That's not pessimism. It's the map. And the map matters because it tells you where the actual frontiers are. The nearest stars, Proxima Centauri, at 4.24 light-years. Alpha Centauri, A and B, at 4.37. Barnard's star, at 5.96. Wolf, 359 at 7.78. Sirius, at 8.6. These are the real targets for interstellar human exploration. The ones where the math is hardest, but not infinitely hard. The ones where fusion propulsion gets you close and antimatter propulsion gets you there. And before committing anyone to a 40-year voyage, you'd want to know what's actually there. Proxima Centauri, B, a roughly Earth-mass planet orbiting in its star's habitable zone, was detected in 2016 using the radial velocity method. It's the most obvious destination in interstellar terms. But Proxima Centauri is a red dwarf, far more active than our Sun, regularly producing flares that would dwarf the largest solar events ever recorded at Earth. A planet orbiting close enough to be in the habitable zone of a red dwarf is close enough to be tidally locked, one face permanently, toward the star, one permanently away. Whether Proxima Centauri b has a magnetic field strong enough to retain an atmosphere under those flares is unknown. Whether it has an atmosphere at all is unknown. Whether any region of it could support human presence is unknown. Robotic precursors would answer those questions long before crewed missions could responsibly be planned. Breakthrough Starshot, a laser light sail concept capable of reaching 20% of light speed for gram-scale probes, could in principle reach Proxima Centauri and begin returning data within roughly 25 years of launch. The engineering isn't solved. But unlike antimatter rockets, it doesn't require fundamental new physics. It requires laser power and materials engineering at a scale beyond current capability, but not beyond the direction current capability is moving. A robotic flyby of Proxima Centauri within this century is plausible. It would tell us what's there. And what's there would determine whether the case for eventually sending people is scientifically compelling or whether we need to look further. One aspect of the interstellar travel question that doesn't appear in physics papers but shapes the whole conversation is the question of purpose. Why go? The scientific motivation for exploring the nearest stars is clear. We want to know if life exists elsewhere. We want to understand the diversity of planetary systems. We want to know if Earth is typical or exceptional. We want to know if the chemistry that produced life here is common or rare. These are questions that robotic probes could partially answer, but human explorers would answer more completely. The history of planetary exploration suggests that humans on the ground notice things that instruments miss, make decisions in real time that remote operators can't, and conduct experiments that weren't planned for because something unexpected turned up. The case for crewed interstellar exploration ultimately rests on the same argument as the case for crewed planetary exploration, that human judgment and adaptability in the field produces discoveries that no amount of robotic sophistication fully replaces. But there's also a motivation that's harder to articulate and more fundamental: the survival argument. An Earth-only humanity is a humanity with a finite future, determined entirely by what happens to one planet around one star. The Sun will remain stable for roughly another 5 billion years. On those timescales, the threats to Earth-based civilization are real but not imminent. Asteroid impacts, supervolcano eruptions, pandemic events of extreme severity, nuclear conflict, ecological collapse. Each of these could threaten civilization on Earth. None of them threaten a civilization spread across multiple stellar systems. A civilization with outposts at Proxima Centauri and Tau Ceti and a dozen other nearby stars is a civilization that can survive the loss of any single system, including the home system. This argument for interstellar expansion is civilizational insurance. It's the backup that actually covers the relevant risk. Not for individuals who won't be alive when the Sun enters its red giant phase, but for the idea of humanity as a persistent presence in the universe. Whether that matters, whether the persistence of humanity is a goal worth organizing civilizational resources around, is a philosophical question that physics doesn't answer. But the physics does answer whether it's possible. And the answer is yes. Within the constraints of known physics, human interstellar travel is possible. Difficult, enormously expensive in resources and time, requiring technologies not yet built, but not forbidden, not ruled out, not permanently beyond reach. That's the answer. The furthest humans could ever travel in space is the nearest stars, and then the stars beyond those, and then the stars beyond those. As far as civilizational commitment and the laws of physics allow, which stops at the edge of the observable universe, but doesn't stop before. The institutional dimension of this question gets very little attention relative to the engineering, but it may be the binding constraint more often than the physics. Human spaceflight has not followed a steady trajectory of expansion since the first crewed missions. It has followed a trajectory marked by ambition, achievement, contraction, and slow rebuilding. 12 humans walked on the Moon between 1969 and 1972. Then, for more than 50 years, no human traveled further than a few hundred miles above Earth's surface. Not because it became physically impossible, because the institutional will evaporated. The technology that sent people to the Moon in 1969 didn't stop working in 1973, when the Apollo program ended. The Saturn V was still there. The engineers were still there. The mission capability was still there. What ended was the political and financial commitment. The Nerva nuclear thermal rocket engines ran successfully on the ground at the Nevada test site. The program was cancelled in 1973, not because the engines failed, but because Congress cut the NASA budget and priorities shifted. The Apollo Applications Program, which would have kept Americans in space continuously through the 1970s using existing Apollo hardware, was cancelled. NASA's Constellation Program, the ambitious return to the Moon, and eventually Mars program announced in 2004, was cancelled in 2010 before achieving any crewed flights. The pattern is historically consistent. Programs that work get cancelled when the institutional environment changes. Getting to Mars will require sustaining a commitment across multiple administrations, multiple budget cycles, periods of public indifference, competing priorities, and the inevitable years when nothing dramatic is happening and the program feels like overhead. Getting to the outer solar system requires sustaining that commitment longer. Getting to the nearest stars requires something that has never been demonstrated in human history: civilizational commitment to a goal that spans not decades, but centuries. Medieval cathedral builders come closest as an analogy. The Cathedral of Cologne was begun in 1248 and completed in 1880. 632 years. 30 generations of architects, masons, and craftspeople working on a structure none of them would see finished. Supported by an institution, the Church, that maintained the goal across human lifetimes. An interstellar program would require something similar. A goal maintained not by one institution across hundreds of years, but by an entire civilization across possibly longer timescales. Whether human civilization is capable of that kind of sustained commitment is genuinely unknown. We've never been asked. But the question of how far humans could ever travel in space isn't only a physics question or an engineering question. It's a question about what kind of civilization we choose to be. Whether we're a civilization that looks at the nearest star 4.24 light-years, 25 trillion miles, every photon of light from it taking 4 years to reach you, and says, "That's too far." Or one that looks at it and starts doing the math. There are people working on this problem right now who don't think of themselves as working on interstellar travel. They think of themselves as working on fusion energy, or radiation biology, or materials science, or plasma physics, or closed-loop life support systems, or genetic medicine. But every advance in fusion energy is an advance in the energy density available for space propulsion. Every advance in radiation biology is an advance in understanding what a human crew can survive in deep space. Every advance in materials science is an advance in the shielding and structural materials that could protect a vessel crossing the interstellar medium. Every advance in genetic medicine is potentially an advance in making the human body more resilient to the conditions that interstellar space imposes. The research programs that will eventually enable interstellar human travel are already running. They're not running as interstellar travel programs. They're running as energy programs, biology programs, materials programs. The application to interstellar travel comes later, when the capability exists and the goal becomes concrete. This is how most transformative technologies develop. The transistor was developed by Bell Labs researchers working on fundamental semiconductor physics. Nobody was specifically trying to build the integrated circuit. The circuit came later, as an application of the physics. Polymerase chain reaction, the technology that makes modern genetic testing and genetic medicine possible, was developed in the early 1980s by Kary Mullis. It won the Nobel Prize in 1993. It was not developed as a component of any space medicine program. It became essential to space medicine because it was essential to biology generally. The pattern is consistent. Foundational research in one field produces capabilities that become transformative in completely different applications. The specific breakthrough that eventually makes human interstellar travel achievable is probably not being worked on right now as an interstellar travel project. It's being worked on as something else, by someone who doesn't know yet what it will eventually make possible. This doesn't mean interstellar travel is guaranteed. It means that dismissing it as permanently impossible because no current technology makes it feasible misreads how technological development actually works. The ceiling isn't static. It's produced by the current state of human knowledge. And human knowledge doesn't stand still. The question of what the very edge of human reach looks like, not the near-term edge, not the century-scale edge, but the genuine theoretical maximum, requires confronting something that almost no physics discussion makes fully explicit. The universe has a structure that actively limits how far any information, matter, or person can travel in a given time. It's not just the speed of light as a velocity limit. It's the expansion of the universe itself. The universe is expanding. The space between galaxies is growing. For objects close enough together that gravity dominates over cosmic expansion, as within the local group of galaxies, which includes the Milky Way, Andromeda, and a few dozen smaller companions, the expansion is irrelevant for practical purposes. The Milky Way and Andromeda are actually approaching each other, on course to merge in roughly 4.5 billion years. But beyond the local group, galaxies are receding from us. The further away they are, the faster they recede. At a distance of roughly 14 billion light-years, the recession velocity reaches the speed of light. Objects beyond that distance, called the Hubble horizon, are receding faster than light, and light emitted from them today will never reach us. They're permanently beyond any form of communication or travel. And because the universe is accelerating in its expansion, a fact confirmed in 1998 by the observations of distant supernovae that won the Nobel Prize in Physics in 2011. That boundary is shrinking over cosmological timescales. Objects that are today reachable at light speed will, billions of years from now, be beyond reach, even at light speed. The universe is closing off portions of itself, permanently and irreversibly, as dark energy drives the expansion to accelerate. This is the ultimate answer to how far could humans ever travel? Not Mars, not Proxima Centauri, not the Milky Way. But the observable universe has a finite, accessible fraction, and that fraction is shrinking. Given infinite time and the speed of light, humanity could in principle reach every galaxy currently within the Hubble horizon. About 2 trillion galaxies. Given finite time and slower than light travel, the accessible fraction is smaller. Much smaller. For any practical human mission, the constraint is not cosmic expansion, but propulsion, biology, and institutional commitment. But it's worth knowing where the absolute outer boundary sits. The universe is not infinite in its accessibility. It has walls that no physics can break. The speed of light is one. Cosmic expansion is another. Within those walls, the question of how far is not answered by the universe. It's answered by us. There's a version of this question that almost never gets asked alongside the propulsion engineering. What does the solar system look like as a stepping stone? Because the furthest humans could ever travel isn't purely a function of what rocket you build. It's a function of the infrastructure you build along the way. The Oort cloud, the theoretical spherical shell of icy bodies orbiting the Sun at distances of 2,000 to 100,000 astronomical units, extends roughly halfway to the nearest stars. We've never directly observed an Oort cloud object in the Oort cloud. We infer its existence from the orbits of long-period comets arriving from all directions at the inner solar system, the remnant signatures of a vast reservoir of material at the outer edge of the Sun's gravitational domain. If the Oort cloud exists as theorized, and the evidence strongly suggests it does, it represents a distributed chain of water, ice, methane, and ammonia. extending from the outer solar system most of the way to Proxima Centauri. Water, ice, can be processed into propellant. A civilization with the technology to navigate to and process Oort cloud objects has, in principle, a chain of resource depots stretching most of the distance between the stars. This is speculative. The objects in the Oort cloud are small, spread across an enormous volume, and finding and processing them with any technology we can currently envision would be extraordinarily difficult. But the concept illustrates something important. The ceiling on human exploration isn't just determined by propulsion technology. It's determined by the entire infrastructure a civilization builds in space over time. A civilization that has been operating in the outer solar system for centuries, that has processed asteroids for metals, extracted propellant from ice-rich moons, built habitats at Jupiter's Lagrange points, looks at interstellar travel from a completely different starting point than we do today. Problems that appear insurmountable from here may look merely very difficult from there. The same asymmetry applies looking backward in time. In 1903, at Kitty Hawk, the Wright brothers flew a powered aircraft for 12 seconds at roughly 7 miles per hour. 66 years later, 12 humans were walking on the moon. Nobody standing at Kitty Hawk in 1903 could have predicted the moon. Not the specific path, not the specific technologies, not the timeline. The trajectory was visible. The destination was not. We are standing at a similar moment now, looking outward. The nearest star is 4.24 light-years away. The propulsion gap is a factor of thousands. The biology isn't ready. The infrastructure doesn't exist. And yet the trajectory is visible. Nuclear thermal propulsion is being flight tested. Fusion ignition has been achieved. Private fusion companies are building compact reactors with timelines measured in years rather than decades. The Mars architecture is being engineered. The lunar South Pole is the next crewed destination. Each of these is a step on the same path. None of them alone gets you to Proxima Centauri. Together, across generations, they might. The Fermi paradox sits at the edge of this question like a philosophical ambush. The galaxy is roughly 13 billion years old. A civilization with modest expansion capability could theoretically spread across all of it in a few 100 million years. And yet, we see no evidence of any civilization that has done this. Either galactic expansion is far harder than it sounds, or civilizations don't survive long enough to attempt it, or we're missing something fundamental about either the physics or the evidence. The Fermi paradox doesn't tell us interstellar travel is impossible. It tells us that if it's possible, it hasn't been done in our galactic neighborhood in any way we can detect, which might mean the problem is harder than it looks. Or it might mean we're earlier to this moment than any other intelligent species in our region of the galaxy, which is its own kind of staggering thing to sit with. Because it means the answer to how far have humans ever traveled might not just be the furthest our species has gone. It might be the furthest any mind in our corner of the galaxy has gone, 250,000 miles. The moon, held for over 50 years. That's where the story of intelligent exploration in this region of the Milky Way currently sits. And that means everything that comes next. Mars, the asteroid belt, Jupiter's moons, the outer planets, the Kuiper belt, the Oort cloud, and eventually, the nearest stars is genuinely new territory. Not new for humanity. New for intelligence. The people who will eventually push that boundary further are alive right now. Some of them are in school. Some of them are building rocket engines. Some of them are running simulations of plasma confinement in fusion reactors or engineering magnetic shielding systems for deep space habitats, or designing the genome edits that might one day make a human being radiation resistant enough to survive 40 years in interstellar space. None of them are thinking of themselves as the people who will answer this question, but they are. Every generation of propulsion technology that gets tested and validated is a door opening, not the door to the stars, one door closer to it. The Wright brothers didn't build the Saturn V. They built something that made the Saturn V eventually possible. The Nerva engineers didn't build the fusion rocket. They built something that made the conversation about fusion rockets for spacecraft serious rather than theoretical. The pattern holds. Progress on the hardest problems in history has never looked like a smooth escalator. It looks like long plateaus and sudden leaps. Decades of no obvious progress and then a breakthrough that changes the frame entirely. Fusion ignition looked like that. The first reusable orbital rocket booster landing on a drone ship looked like that. The first detection of gravitational waves from a black hole merger a billion light-years away, measured by instruments sensitive enough to detect a displacement, 1/10,000th, the diameter of a proton, looked like that. We don't know when the next leap comes. We don't know which direction it comes from. We do know that humans keep making them. So the answer to the title question, how far could humans ever travel in space, is not a fixed distance. It's not a number on a map that physics has circled and labeled maximum. It's a moving boundary, defined at any given moment by the technology and biology and institutional commitment of the civilization asking the question. Right now, the boundary is about 250,000 miles. Mars will push it to 34 million. Nuclear pulse propulsion, if the political obstacles are solved, pushes it to billions of miles, the entire solar system. Fusion propulsion pushes the solar system boundary to its outer edge, the heliopause, and makes the nearest stars a target rather than a dream. Beyond that, the physics is harder and the engineering doesn't exist yet. But the laws of physics don't forbid the stars. They just require that we become something we aren't quite yet. Not just technologically, in terms of how we commit to long timescale projects. In terms of what we're willing to build across generations rather than administrations. In terms of whether we're a civilization that treats interstellar exploration as a civilizational goal rather than a budget line item that gets cut when other priorities get loud. That's the real answer. The furthest humans could ever travel in space is exactly as far as humans decide to go. And we've barely started deciding. When you step outside tonight and look up, you can find the moon without trying. 250,000 miles. 12 people walked there. We're going back. And somewhere in the direction of the constellation Centaurus, not visible from the northern hemisphere, but out there sits a small dim red star at 4.24 light-years. 25 trillion miles. Nobody has been there. Nobody has been anywhere close. But the question of how far humans could ever travel in space is not answered by where we've been. It's answered by what we do next. Good night.